Hello everyone, it's Mr. Wolfe here, and in this video I'm going to be going over example 1 on page 43. So if we look at this problem, it says that a ball is initially at rest and accelerates at a rate of 4.5 meters per second down a ramp. So really quickly, what we want to do is, I know it says down a ramp, and so you might be thinking it's going in the negative direction, but remember, if we're talking about a ramp, whether the ramp is kind of angled like this or like that, really we're saying if it's going to the right, it's going in the positive direction, and if it's going to the left, it's going in the negative direction. And that's just kind of how we've defined it for our scenarios thus far. So is it going to be going in the negative or positive direction based on this information here? Well, imagine it's at rest, right? And then it accelerates at 4.5 meters per second squared. So that's a positive number, which means it's going to the right. So if you imagine an object at rest and something's kind of pushing it to the right, it's going to be going to the right. So it's going to be going down to the ramp this way. It's really, really helpful to draw out the setup of your scenario to make sure that you're kind of setting up your equation right and you're actually solving for what you should be solving for. And it kind of helps to draw this, so if I get like a negative velocity, I know that I did something wrong here. Okay, so in this case, let's just write down everything we know. I know that it accelerates at a rate of 4.5 meters per second or 4.5 meters per second squared. The time in this case, it kind of goes over here, is 3 seconds. And then what it's asking is, what's the distance? How far is this going to go down the ramp? So change in x. So a few things, and so I'm going to circle this because that's what I'm looking for. A few things that I do also know is my initial velocity. It doesn't say it, but like in terms of numbers, but it says that I'm initially at rest. So I'm initially at 0 meters per second. All right, a few things I don't know though yet are well, obviously my change in distance, but my change in velocity, or my final velocity, does not seem to be in here either. So what I could do is I could start to look for what equation am I going to use to solve for this change in or this distance. So I can look at my sheet right here. Always have this out now when you're working on any of these problems. So first thing is, I know that I'm not going at a constant speed because I'm going down a ramp. I'm going to be increasing speed, and it also just tells me you're accelerating. So that means I'm going to have to look at my equations for changing speed. Now notice that I don't have a final velocity, so I can't use this equation. I also can't use these two equations because it doesn't have change in distance, and that's what I'm looking for. So that kind of narrows it down to this one. But that's just kind of the thought process you might be going through when choosing between those three. So here's my equation. I know it says it in this box, but there's more space here. So I'm going to use the equation. My distance, my change in position is equal to 1/2 times acceleration times time squared plus my initial velocity times time. All right, and now it's just kind of plug and chug. I'm looking for that value. 1/2, my acceleration is 4.5. Right, my time is going to be 3 seconds. That's going to be squared. My initial velocity is 0 meters per second multiplied by my time, 3. Now 0 divided by any number is going to be 0, so that gets rid of that. And I'm still going to kind of draw this out just to make sure we kind of get the order of operations down. I see a lot of students messing up on this, especially early on. So don't multiply things first and then square them. Take this value and square it. So 3 squared is 9. So then when you multiply 1/2 times 4.5 times 9, you're going to get a change in position, a distance of 20.25. And the units of that are going to be meters. It's a positive number, so I'm going to just add a positive there because I could be changing my distance to the left. I could be changing it to the right. That tells me I'm changing it to the right. So that's LT1A. Let's go over LT1B now. And I really like this example because thus far it's been sometimes very, very straightforward with proportional reasoning. In terms of, let's say I increase one variable, right, by like I double one variable. Well, thus far it's been, well, the other variable is either going to double or it's going to be half, and that's it. Okay. Now we're going to start to get into a little bit more complicated examples of proportional reasoning. So let me show you an example of that. In this example, I'm only going to be going over the actual numbers method because in class, that's all we did. So the day that I'm making this video, we'll go over the one-to-one method in class. So for my actual numbers method, what I'm going to do is just use the equation that I did before. And it says that in this case, so what I should have done is read the problem a little bit more first. So by what factor must your distance have changed? So I'm looking for this. I'm going to put a question mark there. if the ball's rolled down the ramp for 3 times as much time. So 3 times as much time. This is the thing that I am changing, so I'm just going to draw an arrow towards it. And then it doesn't say anything about my acceleration being the same, but if I'm going down this ramp at the same angle and I'm just going further, I'm still going to be speeding up at the same rate if it has that same angle. So now what I'll do is I'll start plugging in my variables. 1/2, my acceleration, remember, stays the same, 4.5. My time has changed, so my original time was 3 seconds. That's going to be multiplied by 3, so that is going to give me a value of my new time. It's going to be 9 seconds. So I'm going to plug that in right here, and that's going to be squared, plus my initial velocity, which is 0, times time, which is now also 9. But remember, 0 times anything is just going to kind of cancel out. So my change in x is going to be equal to 1/2, 4.5, then I'm going to square that 9 first before I do my multiplying. So that's going to be 9 squared is 81. So then 1/2 times 4.5 times 81 is going to give me a change in position of 182.25 meters. Again, I'm changing my position going to the right, so I made that positive. I'm not going to box that in. I'm going to underline it. The reason I'm not boxing it in is we're not done yet, because in this problem we're looking to see by what factor does your distance change. We just found the actual distance. So when we're doing our actual values method, we have to do the original, the new, divided by the original. So my new is 182.25 divided by my original, which is 20.25. And you're going to get an answer of a perfect whole number of 9. Now let's just say that you did some strange rounding somewhere around here, and you may have gotten, when you divide this, like an answer like 8.999, right? We could pretty confidently assume that that's still going to be the whole number of 9. Okay, so what this is saying is that let's kind of do this down here, even though the question's not asking for it. But we have some space. Is to kind of like take a step back and look at the big picture of this. Is that our cause is we increased time by a factor of 3, and then our effect is that my time, or sorry, my change in position, my distance, increases by a factor of 9. So that's a little bit different of what we've had in the past, right? If I've tripled something, then the other value either goes down by a factor of 1/3 or also triples. Here, I triple it, and then my distance travel is 9 times as much, which kind of makes sense. Like, right, I'm picking up more and more speed. I'm going to be covering more and more distance. All right. So this hopefully gives you guys a better idea of why we need to kind of go through the process with the math on this, is because sometimes you're not always going to go up. If I go up by 3, you're not always going to also go up by 3 as well. So by the way, even though they go up by different amounts, since both do increase, this would still be an example of a direct relationship. Thanks for watching, everyone.